Just going to go through some electricity problems for foundation physics. These are just some exam questions. So our first question here is we're being asked to consider four different charge distributions and then four different areas. So areas 1, 2, 3, and 4. And we have to rank the electric field magnitude from largest to smallest out of these four. So what I like to do first is to just draw my electric field lines for these charge distributions because they haven't been included. So I'll start with this guy here. We know that the electric field lines for a negative charge will be going towards it, because the electric field lines are directed in a way where a positive test charge would move. And because it's a positive charge, unlike charges attract, so the positive charge will be drawn towards a negative. So using that logic, the positive charge must have electric field lines going out. So I'm doing this because it's a smaller charge, so the magnitude of the field will be smaller. And then this guy here will be pretty big, so we can do it for the same as its negative friend below. So what we find is that because this is a positive and positive, and we know that like charges repel, we can say that 1 is probably going to be the weakest in terms of magnitude. Now we can also see this by considering the vectors. You see, if we get this vector here and add it with this vector, we'll get this plus this, and because it's in the opposite direction, they cancel out, so this whole thing is equal to 0. So you can see that from the vector perspective that the force here would be very low. Now, this is probably enough to say that it's probably going to be the weakest because it's the only position that's in between repulsive forces. So we can eliminate A, and then we can probably say that 3 will be the strongest because you have a positive and a negative charge. So, and you can also see the vectors. This one here and this one here are both pointing in the same direction. So it will be a very strong charge in this way. So we can probably eliminate B then. So we're left with C or D, and we can probably say that at 4 and at 2 it's equal because the magnitude is just the strength of the field, not the direction, not the orientation. You can see here they are in exactly same scenarios, just different charges. So I'm going to say that it's C, where E3 is the biggest, and then E4 is equal to E2, and E1 is the weakest. Now, next question here. Normally, household lights are connected in parallel to a power source. Suppose that we have a 40-watt and 60-watt light bulb instead connected in series. Under these conditions, which bulb will be brighter? Okay, so normally with circuits, we would have a DC current, so a direct current, meaning that it would just be coming out of a battery or whatever. But instead, we have an alternating current. And what we need to know is that whether it's an alternating current or a direct current, the analysis of resistors is the same. So we don't have to worry about anything being different. But because these are connected in series, we know that there will be a voltage drop off across the resistors. So we actually need to do a little bit of computations to figure out what the actual power of each of these light bulbs are. So first we can find first we can do V equals I R, but okay, now we would need to use a power equation. So power is equal to IV. So let's look at our formula sheet here. Yeah, this is our power equation, P equals VI, and then by substituting in Ohm's law, which is this guy here, we can get this expression here that we would want. So P equals V squared on R. P equals V squared on R. Okay. Which is equal to V squared on R. So let's say that this is light bulb 1 and this is light bulb 2. So the power in light bulb 1 is equal to the voltage squared over R 1. So we can rearrange for R here by imagining that we will have the triangle here. So this is our V squared, this is our P1, R1. So therefore our R1 is going to be equal to V squared on P1, which is going to be equal to 240 squared over 40 watts. Now the reason why we do this is to find the individual resistances for each of the light bulbs, given its ideal voltage and ideal power here. So this gives us our actual resistance in the light bulb. So 240 over, so it would be 240 squared divided by, what was it, 40? Yeah. So then we get 1440, which seems wrong. That's so high. V squared on R. The voltage. Okay. So do that, and then we find the resistance in the second one. So R2 is equal to V squared on P2, which is equal to 240 squared over 60, which is 960. And then we can find the total current by finding the equivalent resistance. So because the resistors are connected in series, we have that the equivalent resistance is just equal to the sum of the resistances. So this will be 1440 plus 960, so 60 plus 40 is 100, so it's 1500 plus 900, which is going to be 2400. So then we can find the current in the circuit as being equal to voltage divided by resistance, equivalent, because V equals I R, yeah, okay, which will be equal to 240 over 2400. So you can see that this is just 1 over 10, because this is just 24 over 240. you just divide everything by 24, you get that. So you get 1/10 amps. So this is what runs through each of the bulbs. And now that we have this, we put this into our power equation to find the voltage drop off. So since power is equal to IV, and we have no, we would have to do something else. We would have to voltage. We would need to find the voltage drop off, and we would need to use, yes, okay. So the voltage for one, we would have to use Ohm's law again, and this would be equal to I on your resistance of your first one. I we find here, so we use this value here. So this is going to be 1/10 over our first resistance, which is 1440. So this is going to be 1 over 14,400 because I'm just moving the 10 down into the denominator. And then our second voltage will be the same thing, but for your second resistance. So 1/10 over 960, which is going to be equal to 1 over 9,600. And now that we have this, we can find our powers for each one. And we know that power is equal to IV, and because the bulbs are in series, the current will be the same. So we have P of 1 is equal to the current, which is 1/10 times your voltage here. So it would be 1 on 14,400, and P2 will be 1/10 times 1 on 9,600, and we can see that P2 will be a larger number than P1 because 1 on 14,400 is smaller than 1 on 9,600, so our answer is going to be B. Now I feel like you probably can get away with doing this without all of these calculations. It's just what I thought of. So we have a 1.5 volt battery. So our voltage is going to be equal to 1.5. Our energy is equal to 5 times 10 to the 3 joules. So the reason why I'm doing times 10 to the 3 is because we have the prefix of kilo. So a kilo corresponds to times 10 to the 3 factor. So then we want to find our time is unknown, and our current I is equal to 1.2. So we know that the equation for power is going to be I times V. Now the units for this is watts or joules per second. So, or joules per second. The reason why it's joules per second is because current is a measure of charge. So charge is units coulombs over time, so seconds. And voltage is a measure of energy, joules per charge, so coulombs. So when you get these and you times it together, the Coulomb terms cancel out, and you're left with joules over seconds. So that's why watts is equivalent to joules per second. So since we know that, if we get power equals IV, and we multiply it by time, we cancel out with the seconds term, and then we're left with a term for energy. So this times it with time is equal to energy. So let's just apply all of this. So our power is equal to IV, and P times T is equal to energy. So we need to find our power, and then once we find our power, we can find our time because we have an energy value. So first, our power is going to be equal to 1.2 times 1.5, current times voltage. So 1.2 times 1.5, we get 1.8. And then we use this equation here to get 1.8 times time equals our energy, which is this guy here, equals 5 times 10 to the 3. Now to solve for t, we divide both sides by 1.8, and we see that this cancels out, and we have t on its own, so this is equal to t. So we do 5 times 10 to the 3 over 1.8, and we get this value here, 2,778 seconds, because we're all in SI units, and our answer is in minutes. So we have to get our time in minutes to be equal to 2778 divided by 60, because there are 60 seconds in a minute. So then we get our answer, and we divide it by 60, and we get 46.29. So 46.29 minutes, which means that D is our answer. Now this question has a typo in it, and we're going to assume that the direction of your current is going to be from left to right. So this is I. So we want to find which orientation our compass will have after this happens. Now to do this, we will need to remember the right-hand rule and the fact that an electric current produces a magnetic field according to the right-hand rule. So if you put your thumb in the direction of the current, the way that your fingers curl is going to be the direction of the magnetic field. So because the current is going from left to right and my thumb is this way, I will actually have the magnetic field coming into the page. Or not into the page, it will be coming out of the page, it's coming into me. So we need to also remember that a compass, the north bit, the black bit here, will point in the direction of the magnetic field. Now, since the magnetic field is coming towards me, the direction will be pointing this way. I hope that makes sense. A metal wire of resistance R is cut into two pieces of equal length. The two wires are connected together side by side. What is the resistance of the two connected wires? Now this question asks us to use the following formula, which is going to be resistivity formula, this one here. So your resistance is equal to your resistivity, your rho value, times the length of the wire, times the cross-sectional area of the wire. So if you have a wire here, then this is the length, and the area of this circle is A. So R is equal to rho L on A. So R is equal to rho L on A. Now, if we cut the wire in half, our new value for L is now going to be L on 2. So we now have R of 1 and 2 is equal to L over 2 on A. Now, we can times both the up and down by 2, and we notice that this cancels with this, meaning that this is rho of L onto A, which is equal to 1/2, because we can take the half out, rho L on A, and we notice that this term here is exactly this guy here. So this is just going to be equal to 1/2 of R. So the resistance in the two wires is now going to be half of what it originally was. But what's happening is that you have this wire here, and then you cut it in half, and then you now have this half here, and then you connect it with wires to this half here. So now you have a parallel system, which means that the total resistance, the equivalent resistance, has to be added in according to this formula. Plus 1 on R2. So if we just put in our values here, we get 1 on R equivalent is equal to 1 over R1, which is 1/2 of R, plus 1 over 1/2 of R, which is going to be equal to 2 over 1/2 of R, because we can add these fractions together because they have the same denominator. And then we can times both up and down by 2, because doing this multiplication is the same as timesing it by 1. It doesn't change anything. This half cancels with this, and we're left with 4 on R is, so I'll just move down a bit. So we have 4 on R is equal to 1 on R equivalent. So therefore your R equivalent, your equivalent resistance in the entire system is going to be equal to flipping the fraction upside down, so you get R over 4. So our answer is going to be So question 16. As a coil moves to the right at constant speed, it passes over the north pole of a magnet and then moves beyond it. Which of the graphs best represent the current in the loop of the wire for the time of the motion? Counterclockwise current is, as viewed from above the loop, is a positive current. Clockwise is a negative current. So first I'll just draw some of my magnetic field lines. So we need to remember, well, this is a question on Faraday's law of inductance, which states that the induced EMF is equal to the negative of your change in magnetic flux over, the change in magnetic flux over your change in time. It's a pretty confusing formula, and it is derived via calculus, but essentially what it says is that as long as you know the theory, right, that your induced EMF will be in the opposite direction but equal to the change in your flux with time, right? So what happens is that the induced current will be in a direction where the current itself produces its own magnetic field, but the magnetic field will be in the opposite direction of the magnetic field, causing the electric current or the EMF. So what you can imagine is that for the loop to pass over the magnet has um it's directed in a way where it should generate a current going in this direction here, so anti-clockwise. But by Faraday's law of inductance, the induced EMF will have to go in the opposite direction so that this current produces a magnetic field going in the opposite direction of the magnet causing this change. So it's pretty much like a conservation of energy sort of thing. I feel like I explained that pretty poorly, but yeah. So the um the direction of the current, the induced EMF, will be in the clockwise direction first. So we'll be starting off negative. So it's either B or D. But you know that because the flux will increase, the magnetic flux, so will be increasing as it goes over, and then it will decrease as it moves away. So because it's decreasing, this change becomes a negative and a negative, which means that it will be in the positive direction. So what happens is that your current will actually change directions and then now it's positive. So your answer will be D. Um, transformer has 100 turns in the primary coil and 100 turns in the secondary coil. The primary coil is connected to a 240-volt AC outlet and draws 0.05 amps. What are the voltage and current of the secondary coil? So we'll just use our transformer equation, which is this guy here. So VS, I'll just take a screenshot so I can just bring them up here. So this is what we need. Put it over here. So we have, I think that this is meant to be 1,000. It's a typo. So we have that NP is equal to 1000, NS, I'm just going to write down our variables, equals 100. Voltage in our primary is equal to 240. Voltage in our secondary is equal to unknown and draws 0.05 amps. So this is our current of our primary is equal to 0.05. So we have our first equation. We'll do the first half here. Vs over Vp, which is this value here, 240 is equal to Ns over Np, so 100 over 1000. Now what we do is we just times both sides by 240 and that cancels. So then we get Vs is equal to Well, these zeros cancels 1 on 10 times 240, which is just going to be 24 volts. And now we use the second half of the equation, which says that NS 100 over NP 1000 is equal to IP 0.05 over IS, the current of our secondary coil. So I'm just going to flip both fractions. So I'll get 1000 over 100 equals IS over 0.05. And now that I've done this, I can times both sides by 0.05 times that. That cancels, and we get IS. This is going to be equal to 1000 over 100, so those zeros cancels. 0.05 times 10, which is equal to 0.5 amps. So 24 volts, 0.5 amps. Your answer is D. Three particles of identical positive charge and mass enter a region of uniform magnetic field and follow the trajectories shown in the diagram below. Which particle has the highest velocity? What is the direction of the magnetic field? So we're going to need to use this equation here. So actually just do that. So our force is going to be equal to QV sine of theta. So this is a charge of your particle, this is your velocity, and this is your magnetic field, and this is the angle separating the velocity vector and the magnetic field vector. Now, what you would need to have, what we know already is that the force is proportional to our velocity, which means that as velocity increases, our force is increased. So whichever particle is moving the furthest will have the highest velocity. So that means that it's going to be particle C, which means that we can get rid of A and B. Now the direction of the magnetic field, we have to know that the force of this, the force that acts on this particle is going to be perpendicular to both your velocity and your magnetic field vector, while also obeying the right hand rule. So what you would need to do is, if your velocity vector is going right, then you would need to have your magnetic field going into the page so that your force vector will be going down, which is what we need in this diagram, because you see that the projectile is going in and it's moving down. If the magnetic field was coming out of the page, then my hand would be like this and the particle would be deflected upwards. So the answer is going to be C, into the page, because velocity vector this way, if my magnetic field vector, so my velocity vector is there, and my magnetic field is coming out of the page, sorry, so it's coming towards me, so it's actually the, yes, because your velocity there, magnetic field going there, and then your force will be going downwards.